Now for a quick review of the molecular orbitals again, starting with just H2, so just the simple case, we've got our sigma 1s and sigma star 1s orbitals, and those are gerade and ungerade in the stabilizing and unstabilizing case, but that's talking about the symmetry of the orbital wave function that we'll look at in a bit. The sigma gerade 1s is the bonding orbital, and that's the linear combination of atomic orbitals around the A and B nuclei, and we're adding them in the same sense. So it's 1sa plus 1sb, while the sigma ungerade star anti-bonding orbital is the 1sa minus the 1sb. So what we're doing here is we're saying that the electrons are really spending most of their time near one nucleus or the other. And so we expect that the wave function, which is the solution to the Schrodinger equation for the electron, is going to look an awful lot like the wave functions for electrons around atoms, because mostly in a molecule the electrons are still around individual atoms, and so these individual atomic wave functions, these individual atomic orbitals, are going to be reasonable representations of what's going on. So when we look at these, the sigma gerade 1s bonding orbital is this sort of circus tent arrangement with two peaks in the middle of the same sign, and then as a sort of a pass in the very center of the bond between the two nuclei. So the nuclei themselves are located right where those peaks are, and when I draw this sort of circus tent here, what I'm drawing is the wave function along the bond. And remember, the wave function is an expression of the electron itself. The amplitude of that wave function, the amplitude squared, is telling us the probability of finding the electron in a particular place, and the curvature of the wave function is telling us about the kinetic energy. So that's still all within this description here. The anti-bonding wave function, where we subtract the 1s orbital around the B from the 1s orbital around the A, is a kind of a knocked over surface tent, and most importantly, it's got that node there right in the middle of the bond, and that node is a zero crossing. We know that more zero crossings typically mean higher kinetic energy. That's how we count and relate nodes to energy levels in this class, and it's true again. So spatially, that's what it looks like, and it's also, the node means that the electron has no chance of being found exactly between the two nuclei, which seems a little bit silly because that's a place where things are relatively good for that electron, and so not surprisingly that's a higher energy situation. So we make this again out of the 1s orbital, and let's just choose nucleus A here. And the way to think about this is, think about a situation where you have a hydrogen, a neutral hydrogen, with one electron in a 1s orbital, and another proton comes wandering in, a bare proton, just a positive charge, comes wandering in, and we start to perturb the wave function. And there are various possibilities. You can either essentially draw the electron toward the incoming proton, or you can push the electron away from the incoming proton, and those have different effects on the energy. You can basically polarize that neutral hydrogen. So we start with an energy of the 1s hydrogen atom and perturb it. And so we call this a splitting, and we take that 1s energy and we either lower the energy and stabilize it, and that's going to help form this bond, or we increase the energy and destabilize it into that sigma star molecular orbital, and that's of course going to prevent a bond from forming. So the orbital around the 1s just looks like a single one of these circus tents, and again, that thing, what we're doing is solving the Schrodinger equation. Got to remember that. What we're doing is solving the Schrodinger equation, but we're solving it within the Born-Oppenheimer approximation for the electron. So this is the Hamiltonian of the electron, meaning the overall energy of the electron. And psi electronic is the electronic wave function, which is the orbital. So the sigma Gerada 1s, or the sigma star Gerada 1s, is psi for the electron. So it's telling us about the electron, its location, its kinetic energy, everything else, its favorite place to take a vacation, everything is in there about that electron. The protons are located along the axis where we have those peaks, because that indicates a preference for the electron. Remember, the electron really would like to be exactly on top of a proton. That's the energetically most, is infinitely favorable energetically. Unfortunately, that location in space is also infinitely small compared to the rest of space, and it turns out not to be the most probable general location, but it's the most probable individual spot to find the proton. And in the overall wave function, there's two of them. There's a pair, and so they're evenly weighted by the electron because of the requirements of symmetry. We can break this thing up a little more, but first, actually, let's look at that atomic wave function. And again, remember that it just decays like an exponential. So the wave function for a 1s is just e to the minus rho, where rho is the distance scaled by the Bohr radius, which is about half an angstrom. And so the electron near a single charge is pretty much always going to be of order a half an angstrom or so away from the nucleus in its most probable distance. And that's just scales. It's basically always true because the last electron into a neutral atom is always going to see a charge that's around +1. And this Bohr radius, the A naught of half an angstrom, is just the scale distance away from a single positive charge that an electron will tend to locate itself. And when we construct the molecular orbital, we get a mutual interaction distance. It doesn't do too much good to get much more than a Bohr radius away, or much closer really than a Bohr radius together for those two protons. And in fact, when they situate themselves about 2 Bohr radii apart, they can basically reach out and touch each other with the electron density, and they can kind of lock hands. And that's exactly what happens. So that is why a chemical bond is pretty much always of order an angstrom. It's scaled into the system. That highest occupied molecular orbital, that last electron or two in the problem, is basically seeing +1 charges all over the place, because there are a lot of other electrons that are really, really close to those nuclei and really do pretty much just think they're in atoms, and they're shielding off most of that charge most of the time, and what you're left with is a situation where electrons have a distance of about an angstrom. If you double it up so they can just kind of the wave functions reach out, and you get this kind of circus tent arrangement to things. That's the optimal arrangement from the point of view of the electrons, and it's overall optimal because we have to deal with the nuclear repulsion of the charges as well. So let's take a little bit of an excursion here and think a little bit more about what that wave function is saying. So here's a kind of a cut through this, and I've drawn a couple cuts. We have the positive charges. What I've drawn for this kind of circus tent, again, that is the progression of the density of the wave function, the probability distribution of the electron. If I move right along the axis. So if I move away from the axis, you're going to get a smaller value of the exponential. You're not going to see that really peaked circus tent where you imagine the pole is poking up, which is where the nuclei are. You only get that peak, that cusp, when you're really right on top of the nucleus. So as you move away, in addition to what we call the axial direction, which is the z-axis, the direction of the bond, you can move radially away from that system, and you're going to have essentially a tube of electron density that still reflects. It's going to reflect essentially the distance away from the nucleus in the radial direction. It's going to decay away with about a Bohr radius as well. because the whole thing is reflects how close the electron is, in fact, to that nucleus. So now if we look at the wave functions, again, remembering the importance of the curvature to the overall energy, again, to emphasize that basically what's going on is when I make the 1s sigma Garada wave function, I'm taking the curvature that that intrinsic exponential had, and by having the wave function not go down as far in that interval between the two peaks, between the two protons, I have less curvature than I would have had otherwise. That less curvature also is what we call electron delocalization, and it means lower kinetic energy for the electron. Whereas in the sigma star Ungerada case, where the signs of the wave function around the two nuclei change, then I have that zero crossing. I have a node, and the wave function actually is steeper than it would otherwise have been if I didn't have the nucleus, the other nucleus there, because it has to switch sign, and that acceleration of the decrease in the value of the wave function as I go from one nucleus toward the other nucleus, that acceleration is a higher second derivative, which means higher kinetic energy, and you have the overall energy going up. So the sigma is stabilizing, the sigma star is unstabilizing, and you notice I always draw them basically evenly split about that original 1s, and that's entirely intentional. The difference in this, what we call splitting, is very, very close to symmetrical. The consequences for the beneficial consequences for the curvature in the 1s sigma Garada are about the same, but of the opposite sign as the disbenefit of the increased curvature in the sigma Ungerada star antibonding orbital. It also turns out that almost always there's a little bit more trouble in the sigma star, so it's actually kind of delta plus epsilon. There's a little more destabilization than there was stabilization, but it's a small term, and for this class it's not really important at all. So that splitting is always pretty much symmetrical there. The last thing now is we're still talking about this pretty much from the perspective of the electrons, and we got to remember that to bring these protons together, even before I start delocalizing the electron, if you imagine the proton next to a neutral hydrogen atom and a single bare positively charged proton, and if I don't let the electron move, so I have a 1sa as we have over there on the left for that atomic orbital, and all I'm doing is bringing a proton closer and closer and closer to the other nucleus. If I refuse to let the electron adjust to that at all, then the only thing that's going to go on is the two protons are going to fight each other. And so that destabilization there is in play, and that is the nuclear repulsion. So you got to remember, when we draw these electron correlation diagrams and we show all the splitting and everything, that is splitting from the electronic perspective, but into this you add the nuclear repulsion. So you only get an overall bond, even if you have a net stabilizing effect of the electrons, if that electronic splitting delta there in the sigma Garada bonding molecular orbital is more stabilizing than that nuclear repulsion term, as I've drawn it here. So the overall step from the infinite separation to the having two electrons or even one electron in the sigma orbital is net beneficial. And if it wasn't, you wouldn't get yourself a stabilized bond. So we draw the molecular orbital correlation diagrams from the perspective of the electron, but we have to remember within the Born-Oppenheimer approximation that the piper is still to be paid. We have to go in the end and find that nuclear repulsion and add that back on, and that in the end is what determines the overall energy of this system.